Hey, JSOURCE, impersonation here. What is a bridge? Bridge stands for bridge, ridge, idge, dj, nga, air. But where did bridges come from? The first bridge was invented in 1912 by Jonathan Bridge when he got tired of falling to his death whenever he tried to cross a canyon. So we built the bridge. Bridges were a huge success and went on to inspire Simon and Garfield's song Bridge Over Troubled Water, in which the cool feline tells his owner about the bridge. Now, before we can actually tackle the problem of Tacoma Bridge, we need to understand a few key principles first. Key concept number 1, natural frequencies. Now, before we can understand what a natural frequency is, we need to establish what a frequency is. In waves, the frequency is equal to how many cycles per second. Because the wave speed is equal to the frequency times the wavelength, that would mean that the frequency is equal to the wave speed divided by the wavelength. The wavelength is the distance between two peaks on a wave, and it's expressed in meters. Now, in a wave, where the wave speed and the wavelength are constant, the frequency is also constant. So this is the natural frequency. The next key concept that we need to understand is wave superposition, but to understand wave superposition, we need to understand another key concept named phase differences. Phase differences are expressed in degrees, and they rely on two waves having both the same frequency and wavelength. Phase difference describes the comparison of where two waves are in their own respective cycles. If the two peaks line up, then those waves are known as in phase and have a phase difference of 0. If the peaks and the troughs line up, then the waves are known as out of phase and have a phase difference of 180. So, if our two waves are in phase, with a phase difference of 0, then we encounter positive interference where the two amplitudes add together. However, if our two waves are out of phase with a phase difference of 180 degrees, then we encounter negative interference where the two amplitudes take away from each other. For example, if two waves have the same amplitude and are in phase, then the amplitude overall will double. However, if the two waves have the same amplitude and are out of phase, then the overall amplitude counteracts to make it 0. Essentially, when we get wave superposition, the amplitude either increases or decreases.
Over yonder, what do you see? The sun is rising, most definitely. A new day's coming. Ooh, people are changing. Ain't it beautiful? Ooh, crystal blue persuasion.
Slinkies are incredibly interesting if your interests happen to be incredibly boring, which, unfortunately for you, mine are. Slinkies are incredibly useful in physics because they allow us to visualize waves, like this one. There are many aspects of waves that we could analyze and go into the nitty-gritty with, but today we're going to be mainly focusing on frequency. This wave has quite a long wavelength but a relatively small frequency. This is because wavelength equals wave speed divided by frequency, so they have an inverse relationship. So if I were to increase the frequency, I can reduce the wavelength. I can increase the amplitude while having zero effect on frequency. When I release the slinky from a height, it has a high initial displacement and therefore a high initial amplitude, but over time, this amplitude gradually decreases. The amplitude tends towards zero but never really gets there, whereas the frequency stays the same. Because of this, we can say that no matter how small the amplitude gets, the frequency is constant, making this the resonant frequency. With a decent understanding of resonance, we can now move on to flutter, more specifically aeroelastic flutter. Resonance is a subcategory of flutter, and although all resonance is flutter, not all flutter is resonance. Flutter is movement in a system caused by an external force. So, by this definition, both resonance and aeroelastic flutter fall under this category. But here's the key difference between resonance and aeroelastic flutter. Resonance is caused by shaking in one system causing shaking in another system, whereas aeroelastic flutter is caused by a force acting on an object. So, resonance would be a sine wave generator hooked up to a spring with a mass on the end of it, whereas aeroelastic flutter would be a force acting on a wing of a plane, such as airflow. As air rushes under the wing, it causes the angle to change, meaning that then air rushes over the top of the wing, pushing it back down again, and this just continues and continues and continues, giving us an aeroelastic flutter. If a wind with a similar frequency to the fluttering then sweeps into the wing, then we encounter both resonance and aeroelastic flutter. Mark Barton of the University of Glasgow explained these two concepts pretty simply. Resonance is a periodic response to a periodic force where two frequencies are quite similar. Aeroelastic flutter is a constant uniform force acting on an object rather than a periodic one. In 1895, a young man named Leon Moiseev graduated from Columbia University with a degree in civil engineering. He quickly became a pioneer in the development of suspension bridges. As an expert in the field, Leon was able to rent quite a lot of his time to working on the Golden Gate Bridge, where he took a lot of his concepts from paper and put them into reality. And now, the year is 1937. The Golden Gate Bridge has just been completed by a team of esteemed engineers. Among them is Levi Medal recipient Leon Moiseev. Having seen the Golden Gate Bridge, Tacoma wanted one of their own, so they went straight to Leon. Tacoma was nowhere near as rich as San Francisco, so this really pushed Leon to his limits. So, in order to cut costs, Leon opted towards girders rather than trusses. Trusses are tessellated triangle beams which allow airflow through the gaps, whereas girders, on the other hand, are just these solid sheets of metal so no air can pass through. Because trusses allow airflow, this means that forces don't build up on the underside of the bridge, meaning that there's no aeroelastic flutter. But with girders, well, in that case you've essentially just got a giant parachute for air. Girders do absolutely nothing to prevent aeroelastic flutter, because they just act as a giant parachute for all the air to bash into and cause forces to lift the deck up. Because girders don't allow airflow, this allows for forces to act on the underside of a bridge and cause oscillations to just run rampant throughout the whole structure. Throughout construction, it was immediately clear that the bridge just wasn't fit for purpose, as even construction workers would note on the bridge shaking constantly, giving it the nickname Galloping Gertie. Though already too much time and effort and work had already been put into the bridge, so they just kept going with it. Engineers and physicists alike immediately started looking for a solution to the rampant shaking. One solution that they came up with was drilling holes into the girders to essentially turn them into trusses, but this was instantly ignored by the council. There were also plans to make the underside of the bridge more aerodynamic in order to alleviate the forces acting on it, but the bridge collapsed way before they could do this. Because the movement was caused by the wind, this meant that both the bridge and the wind were in phase, meaning that they could resonate with each other. Of course, positive interference causes an increase in amplitude, so if we apply this to the bridge, it just means that the oscillations get more and more violent over time. The whole structure became trapped in a positive feedback loop until it had no other option than to eventually just break. Fortunately, no human life was lost in the incident, although a dog did fall to its death inside of its owner's car. And so, just like that, years of toil and labour lost over a matter of either ignorance or arrogance. Mankind had decided that they were too clever to double check, and were once again put back in their place. Tacoma was a reminder that negligence, motive with both best or worst intentions, are equal. They always conclude in failure. Much like this video. Still, disaster is more of a side effect of innovation than the direct result of it. Despite the bridge still being in scraps, the residents of Tacoma still required a way to pass the gorge. And so, in 1951, the second bridge was constructed. This new bridge still stands as a testament to lessons learned, using trusses rather than girders and using steel beams for support. Due to materials being in short supply during World War II, the materials used in the first bridge were recycled for use in the second. So, technically, parts of the original bridge still stand to this day. And to me, this says more about human ingenuity than anything ever could. Forever strolling into an infinite minefield of check yet never ending in mate. Such is the means of betterment. If you Google Leon Moiseff, his failures come up before his achievements. Can you think of a greater insult? He decided to cut corners. Why? He did it in the hopes of advancement. Did we advance as a result of it? Yes. We made progress out of a man now scorned by history. We became better as a result of it. Just because a failed does not diminish the return, and, in fact, I would argue it increases it. Leon had made great successes on the Golden Gate Bridge, which are now completely overshadowed by the seeming ignorance of Tacoma. Seeming. The word seeming tells you everything you need to know about a perspective. It is incomplete, unfair, one-sided and unseeing of the whole picture. This was not ignorance or arrogance or negligence, but rather an attempt at an engineering revolution. The word progress comes from Latin, meaning to move forward in the face of trial, to maintain momentum through obstacles, even if the velocity be a Planck length per millennia. There is no devolution in development. I'd wanted to conclude that the failure of Tacoma was the fault of an underqualified, overconfident engineer who flew too close to the sun. But I can't find any way in which to do so. Could have Leon been acting naively? Maybe. Could have it been the fault of institutional greed? Maybe. Will we make the same mistake again? No. For that, Mr. Moiseff is a progressor. Yo, you made it to the addendum, I guess, which means that the video's thankfully almost over. I'd wanted to make the whole thing just purely based around physics, but in order to make it more interesting to a wide group of people, I needed to present it like a story with characters, which it did have, but maybe not to the same extent. And also, telling the story of a disgraced engineer who I think is a true icon. It just has a good hook to it for the ending. It just makes a good conclusion. Some of the B-roll is taken from YouTube, others from VidEasy. I don't know the legal stuff behind it. Yeah, that's about all, so I hope you enjoyed the video.